Alright, so I'm going to try to explain ROP chaining in a simplified way, which is how I best understand it. So, say that you're given some function stack that takes in user input and you have a buffer at some arbitrary address. Well, if you wanted to perform a traditional buffer overflow, something you could do is just to overwrite the buffer, overwrite the RBP, the stack frame pointer, and then overwrite your return address for the function to some arbitrary function. In this case, we want to go to func1. But the issue is that if we do that and say that we successfully overwrite the return address, we end up here at this OX206, and we can go through the function, but the issue is that here we may come across a function that required previous function, or we may come across instructions that required previous functions to set registers a certain way, which means we may not get the output we want. Execution may be blocked. Maybe this is some kind of protection against this. And in this case, you would use ROP chaining. So the way you would perform a ROP chain is, first you want to find the gadget, and the gadget is just a group. It can be a single instruction or a group of instructions that are basically like a puzzle piece. You put these instructions together. You can reuse them if you want as well to get to do an overall goal. So let's just say that we find the address to some gadget, this being something that alters RDI and then goes somewhere. So what we can do is we can override our buffer with junk, like a bunch of A's, and then we will end up overriding our RBP register, but in this case, because we're not going back to this function, it doesn't really matter. So we're going to overwrite that as well, and that turns out to be 28 bytes. Okay, once we get to our return address, we have to go to our first gadget, and because we know what we want to do, we want to go to some place. So our first objective is to set the RDI register to something, and secondly, we want to go somewhere. Now, how do we set RDI? You could do a move, but that would complicate things. If you look at your fundamental instructions for something like x64, you have pops, and then some kind of register like RDI. And sometimes, if you use a tool to find these gadgets, you'll find a pop RDI followed by a ret. Now, what this basically does is it'll go to your stack, your overall program stack. It will pop the topmost thing into RDI, and presumably you would set that topmost value by overflowing your stack and then writing. Okay, so once you overflow your stack, all of this is for you to use. This is where your ROP chain comes in, and then you would return somewhere, which would also be in this kind of space that you use for your ROP chain. So let's just assume that you use ROP gadget to find a series of instructions like this: pop RDI and ret. And let's just say that you happen to find them somewhere in program memory at address OX105. And this may look like a weird series of instructions, but this gadget is most commonly used for setting a register and then going somewhere. So what we could do is, instead of setting our return address to go directly to func1, we could set it to go to this address of OX105. So let's just draw what that would look like. So this would go to G1, our gadget, and then we still need to set RDI to something, because this ret address is going to be popped off the stack when the ret of the function that we're doing goes from wherever it is in memory to here. So we have to account for that. So after this ret address to here, what we're going to want to do is get our value for RDI, because right after that ret for that random function, the next thing directly is that pop RDI, so we want to account for that. So what we can do is set the value which we want for RDI, which is this 0, 1. So we can just put the 0, 1 here, and then, okay, so we did this. Now this ret instruction is going to execute. So now where do we go? Well, we want to go to the beginning of func1 because we set RDI for func1. So then this would be the address of func1. Okay, so this is kind of how the execution would go. So let's just say that we overwrit our buffer for some function, and then that buffer goes to the end and it executes a ret. So that ret is going to get this address. It's going to pop it off the stack. So we can just cross that out. And then this isn't really a great visual, but because the stack grows down or grows to lower addresses, but just for the sake of understanding how ROP works, just assume that this is kind of how the stack works. So it pops that off, and then now our instruction pointer is here at this OX105. Okay, we'll pop RDI as a stack function. So what's the newest thing on our stack? The 0, 1. So this 0, 1 is going to go from this pop, it's going to end up in RDI. So now RDI is set. Okay, so that pops 0, 1 off the stack. Now after this pop, we have a ret, which takes us wherever it takes us to whatever the topmost address is on the stack, and currently the topmost thing on the stack is the address to func1. So that ret is going to pop this address from the stack and then take us here. Now you can really choose any address you want. For more complex ROP chaining is where you would go to other gadgets, so something like this, but say other instructions if you want to do something more complex. But for the sake of this presentation, we're just going to say that we want to go to function 1. So this ret is going to take our EIP pointer, go to the beginning of func1, and these instructions will execute, like push, RBP, all that kind of stuff. And this is also under the assumption that our RDI register isn't altered. So it'll go through its execution, and then we'll get to this compare 0, 1 to RDI. And because in our ROP chain, our gadget sets RDI to whatever was at the top of the stack at the time, which was 0, 1, because we put it there, we'll pass the compare, and then we'll jump to the win function. Now when it comes to actually writing the ROP chain, it would look something kind of like this. So as we stated previously, our goals are to overflow our buffer plus RBP, and then we want our return address not to go to a function but to a gadget, which is again a series of instructions, a small snippet of instructions that do what we want by setting registers or going places. And the way that we interact with those gadgets is to put those desired values and addresses on the stack for those gadgets to interact with, or to get that from the stack. And then as well, we put the value for a gadget, as we said, that 0, 1, and then the address of where we want to go next, because again, after that 0, 1 is popped, the next thing on the stack will be fed into ret. Now if you wanted to do this to write this in like a real program, what you could do is first overflow your buffer and RBP, and then set that 8-byte, because this is a 64-bit. ROP works best with 64-bit. You want to write in Little Endian, because that's how most Intel machines store data on the stack, the address to your first gadget, which we said was 105. So that's the 8-bit representation of 105. And then secondly, the value that you want to go into RDI, which is 0, 1. And then lastly, where you want to go after the pop, which is 206, which is the address of func1. Okay, so here I'm going to do a little bit kind of a little bit more of a realistic explanation. This is the general idea, but here I'll do kind of a more in-depth explanation. So say that say that the stack goes downwards, and this is our 28 bytes, or I'm sorry, our 28 bytes would fill the stack up towards higher addresses, but say that the stack goes downwards in this case. So after these 28 bytes, the next thing on our stack would be our address to our gadget 1, and then it would be our OX01 for the value of what was it, RDI, and then lastly the address to func1. So say that you've overflowed your buffer in the arbitrary function, and then you get to, so generally in x8 and x64 what will happen is a leave and then a ret. Now this leave is the reason why the next thing on your ret is the address that you gave. So here, as we stated before, is RBP. Here, I'll write this in red. RBP. Now this leave, what it's going to do is it's going to move the stack pointer, which is RSP. It's going to move it to where RBP is, so ESP will be here now, and then it's going to pop RBP off the stack. So this junk RBP is going to go out to the register itself, because that's how the stack call fixes itself. And then now what's at the top of your stack is this address to the gadget, and that's what ret1 is going to use. And then once you get to the gadget, you get your pop RDI, and then because this was popped, the next thing that you implemented in your original ROP chain is a 01, and then the ret after the pop will go to func1. So really, best practices when it comes to ROP chaining is to target look for gadgets that come at the end of instructions, because the way that you're traversing through things generally is this ret. You look for things that set things. So if you want to set a register to something, look for something that does a pop register followed by a ret. There are more complex techniques that you don't use rets entirely. You use stuff like unconditional jumps and even calls, and there's even more complex techniques such as like block ROP, where instead of using single instruction as gadgets, use entire blocks of code. But generally, this is an easy way to understand ROP, and how I feel, and this is how I feel is an easy way to understand it, because ROP is kind of a complex thing. So yeah, I hope that you got some value out of this, and if you enjoyed it, then check out other stuff like on my GitHub. So thanks.